Hi everyone, I'm Kim and I'm one of the 111 TFs this year. And in preparation for the midterm, I've decided to film a series of videos where I solve the midterm from 2019. This was the midterm I took when I took this class, and I remember it being a little tricky, so I'm excited to revisit it. I generally say before you watch this video, try to read the question and have a stab at it yourself so you can get a little emotionally attached to the problem, and then come back and watch this video. So hopefully it's a little more meaningful once you do. So I'll go ahead and get started. So first I'll read the question. So we have particles emitted by a radioactive source one by one with the time gaps between successive emissions being IID expos. So that seems important. IID expos with mean parameter beta. And rate parameter 1 over beta. So the time to emission of the first particle is exponential with mean beta, the time that elapses between the emission of the first and second particles. So all of our inner arrival times are have mean beta or rate lambda. Jenny, a physics student, records the first n inner emission times on her laptop, but on her way from work, her laptop gets stolen by someone who bought. Okay, so I think that's a reference to the AirPods stealing case from a few years ago. But basically, Jenny can only recall the total time t that elapsed until the emission of the nth particle. So no more inner arrival times, just the entire time. It is critical that she obtain an estimate of beta so she can move on to the next stage of experimentation. So we're going to help Jenny out. So first, I guess like to summarize what we learned there, we have a bunch of like IID expos like y1 ... yn, and these are going to be expo IID with mean lambda. And then we only know t, which is the sum of all of these guys. And if you recall, the sum of expos, the sum of n expos is actually distributed gamma n comma lambda. So that's something hopefully we've seen pretty often from 110 and maybe from 111. If you wanted to draw this, I like drawing my Poisson processes. So we kind of have like x's on a number line, and each inner arrival time is expo. But note that like the sum itself is not going to be expo, it's going to be gamma. Okay, so find the MLE of beta. So the first thing you generally do when you see MLE is write a likelihood down. So we're going to write that down. So likelihood of beta given the data is equal to the joint PDF of y. But instead, we don't actually know the full data set. We want to do this all in terms of like what we know. So right now our data is t. So this is going to be the PDF of t given beta. And I just wrote down this that tells us that it is gamma and lambda. So now we're going to want to write down the PDF of that, and you can like scroll up to your distributions here, and we have, it looks kind of like this. So we have gamma over a, -1 lambda x, blah, blah, blah. Okay. So in terms of our, like right now we have gamma, like we have gamma n lambda. So that's going to be gamma n to the -1, lambda x to the n, e to the negative lambda x, and then x to -1. So, and we're going to be plugging in like t. So we have everywhere we see x, we're actually going to put a t there. So I'm going to put like a big T here, big T here. Great. So now I'm going to transfer that over. I can use the magic of iPad to do that. Okay, and now I want to drop a bunch of constants. So first, like we know n and we know t, so we're going to be able to drop constants that are just involving n and t, but not involving beta, all the multiplicative constants. So one thing we can drop is this guy. We can also drop these. Oh, and I forgot to put a t here, but this has a t too. And we can actually split this up into lambda n, tn, so we can drop this tn. So what we have left is lambda to the n, e to the negative lambda t. Yeah, so that's our likelihood. Now, as usual, we're going to take the log, get the log likelihood. So the log of this given t is going to equal n log lambda minus lambda t. And then we're going to take the derivative. So our score function, which is equal to the partial of L with respect to beta. This is going to be, and now we have this in lambda. So I want to replace lambda with beta. So one thing we know is lambda equals beta, like to -1. So this here is going to equal n log 1 over beta minus t over beta. So now I can take the partial with respect to beta. So this is, and I did all of that by invariance of the likelihood. So that's how that works. We can safely do things like that. Yeah, one more transformation, I guess I would turn this into negative log beta. Cool. So now taking the derivative of that, I have negative n over beta, and then plus t over beta squared. That's some calculus. And then now I'm going to set this guy equal to 0. I can cancel out a beta, and that should help with solving. So I get negative t plus t over beta equals 0. I can cancel out because there's a 0 on the other side. And then if you solve for this, I get beta hat equals t over n. So that's what we have for the first part. See, is there anything else? It just asks for the MLE, so we're done there. Okay, so now I want to find the MLE of the variance of this MLE. So I'm looking for variance of beta hat, and this equals variance. And recall that all estimators are functions of the data, so the randomness comes from the data. So we have variance of Tn, and then n is a constant, so I can pull that out. So 1 over n squared variance t. And then the variance of t, well, I have that t is distributed as gamma over gamma lambda. So the variance, if I look up here, is going to be n over lambda squared. So I have 1 over n squared times n over lambda squared. And then I probably want to convert that to betas. This is going to be 1 over n lambda squared, which is equal to beta squared over n. Cool. So that's our variance. And now the next question asks for the Fisher information. So Fisher information of beta, this is equal to the variance of the score of beta given the data. So we already have this score. That's why I'm going to just go ahead and write it. And staring at this doesn't look too bad to take with take the variance of it. If it does end up looking a little gross, you can probably take another derivative of the score function, take the negative expectation via the information equality. So here we have variance negative n beta plus t over beta squared, and we're taking this variance with respect to like the variance, the randomness of this variance comes from the data, not the parameter, because sort of frequentist vibes. So this stuff here is a constant, so this is going to be equal to variance of t over beta squared. We're considering beta to be a given, so we have 1 over beta to the 4th variance t. And then now we want the variance of t, which like we sort of have up here. It's just n over lambda squared. But note that this is going to be n over lambda squared, which is equal to n beta squared. So this is equal to n beta squared over beta 4, which equals n over beta squared in total. So there's our Fisher information, which is pretty fun. I guess like something cool about this is that like I don't know if I would have immediately thought of this on the exam, but it's mentioned in these solutions, and I think that's kind of cool. So the exact variance of the MLE is this thing right here, beta squared over n. And we know the CRLB, the Kramer-Rao lower bound, or also like 1 over Fisher information, that's going to be the asymptotic MLE variance. And that's this exactly here. So in this case, the asymptotic variance actually is the true variance, which is, you know, not always true, but in this case it is. That's like a fun fact. You probably don't have to mention that to get like credit on this question. Okay, so next is D. Jenny is not very familiar with statistics. How would you explain to her what the variance from B means? So the variance from B, that's the variance of the estimator. So we have like, what does a variance of an estimator mean? Next is, why should she care about this variance? Is this variance the variance of the maximum likelihood estimator, or the variance of the maximum likelihood estimate? Well, I'm going to go ahead and answer that last one. This is the variance of maximum likelihood estimator. So estimators are a function of your data. They have not crystallized to anything. Estimates are numbers, so estimates have variance 0. So yeah, that should be like a pretty, you should repeat that mantra in your head, like estimator can move around. It's like before you plug in, and then it becomes estimate. Okay, so how would you explain to her what this variance means? I personally seem to have not gotten, I got some points on this, but I think I missed one of the keys. But basically, so one of the keys here is that we're doing, like, I guess after repeated experiments is key. So we're going to do a bunch of experiments, and those are all independent experiments. And we're going to get a bunch of like T's from these experiments, and then you're going to get a bunch of beta hats from these experiments. After this is all like repeated over time, this is how much your estimate will actually like vary. So it will, the word in the solutions is fluctuates. That's a fancy word to me, but like, I guess after repeated experiments, this is how beta hat fluctuates. Like we have a bunch of beta hats, maybe beta hat 1, beta hat 2, ... And yeah, so that's what this variance of the estimator means. Why should she care about this variance? So the variance is always a contributor to the MSE. The MSE, if you want to recall, is bias squared plus variance. In this case, this is unbiased. So this is actually going to be bias 0. So the MSE is equal to the variance in this case. And the MSE is like one of our metrics for a good estimator. So when the variance is a little lower, we would believe that our estimator is doing a better job. Our estimator is kind of hitting the mark, so unbiased, and it's also not straying too far from the true parameter. So that's why she should care. Care because low variance means low MSE. And I think, yes, that's answering all of those questions. So it is variance of the MLE estimator. After repeated estimates, this is how the estimate will fluctuate around the true. And then we care because of the low variance and MSE stuff. Okay, so finally, Jenny is concerned that the MLE estimate you give her could be improved if only she could cover her laptop, discuss whether this is worthwhile. So what we're going to do here is now we're going to pretend we do indeed have all of the data. So in this case, we're looking for L of like beta given the entire data, which, does it give it names? I gave it names Y up here, so given Y. And this is going to be equal to the joint PDF of Y given beta, which is equal to this I equals 1 to N F of Yi, where our Yi's are expos. Beta, and this is going to be e to the negative lambda lambda to the Yi over Yi factorial. And then you're going to want to convert to betas eventually, but now I'm going to just drop, I can drop this because it's just Yi's, and this ends up being proportional to e to the negative n lambda, lambda to the sum Yi's. Oh wait, it seems that I might, I did the Poisson accidentally. I kind of autopilot to Poisson. Wrong PDF. So our PDF is actually this guy, my mistake. Lambda e to the negative lambda x. I did the Poisson because every time I do an example, I do a Poisson. So we have lambda e to the negative lambda to the yi in this case. Yeah. Whoops. I made you watch that. Okay. So it's like mostly the same. Like we have lambda to the n e to the negative lambda sum yi's. And there's no constants that drop off. We just have this. And then we can replace it with betas. So 1 over beta and e to the negative 1 over beta sum of yi's. So if you look at this, like our sufficient statistic is actually going to be sum of yi. And this is equal to our total time t. So our maximum likelihood estimate is going to be a function of the sufficient statistic. And we can kind of see that like one way to interpret the sufficient statistic is how much, like what function of the data should I ask for in order to construct the likelihood function? And indeed, it's just going to be the total of the yi's. Let's see if there's any other gems of knowledge from the solutions. Yeah, so that's kind of it. Okay, so discuss whether obtaining the better estimate. It's not because we have like a sufficient statistic. Cool. So that's it for this problem. It's been like 20 minutes. That's like maybe a little slow, but hopefully you have a good idea of what's going on here. This is very basic, kind of start with likelihood, do a little bit of analysis of the estimator, and maybe talk a little bit about sufficient statistics. And that's it. So I'll see you guys on the next problem.